Okay, hello to everyone who has just joined. I think we can start the webinar now. So my name is Silvestros Vlachopoulos and I'm a senior analyst at Delta EE. I would like to welcome you to today's webinar, in which we will discuss some highlights from Delta EE's new service, the distribution network service, where we looked at some of the practices used in the UK and the Netherlands with regards to integration of renewable generation. Now, I'm joined in today's webinar by Mr. Lars Senkel from Aleander. Good morning, Lars.
Good morning, Professor.
Let's start with a few housekeeping rules. The webinar is expected to last about 30 minutes. We'll also give a few minutes dedicated at the end for a brief Q&A session. That being said, you can write down any question that you may have during the webinar. You can look at the screenshot that we have here on the presentation for how to do that. So we will try to discuss your questions at the end, but if we don't have time to address all of them, we will reach out to you after the presentation is over. Another reminder here is that the webinar is being recorded, which means that if for whatever reason you have to drop off and do something else, you can still continue to listen to it at a later stage. And we'll send some slides with the presentation after the presentation is over. So you will have access to all the content. Now, let's start the sort of conversation with a poll. We usually have polls in our webinars to start the interaction with the attendees. The poll that I have ready for today it has the question of how big of a challenge is integration for renewable energy for DSOs. There are 4 options depending on how big of a challenge do you think it is. Let me launch the poll. It should be open now, and you can choose one answer. A reminder also that no one else can see what you voted, so it's being anonymized. We'll give it a few more seconds. I see that about 80% have responded. Okay. So I believe that now you can see the poll result. So it's a very close math, as I see it is. About 50% believe that it's the biggest current challenge for DSOs. An equally high percentage believe that it is definitely a challenge, but there are currently bigger challenges for DSOs. And we also had a few people who answered that it is not yet a challenge in my country. This is understandable because not every country has a significant amount of renewable generation yet. And very few answer that they are in control of the challenge, and so it's not a very big concern anymore. I would say that the results aren't really that surprising. It is one of the hottest topics, I guess, with regards to the energy transition and the role of DSOs. So moving on to the webinar. And let's start off with a very brief introduction of Delta EE and Aleander. On Delta, as many of you may know, we are doing research on the energy transition. This particular webinar, as I said earlier, draws on content from the new distribution network service, which I highlight on rectangular here. And this service, we are doing this in support from Aleander. Now on Aleander, Lars, would you be okay to give me a very brief introduction on the company, a couple of sentences, because not everybody may have heard of Aleander.
Yeah, sure, of course. So Aleander is basically a group of companies, which includes Aleander, which is the biggest distribution network operator for electricity and gas in the Netherlands. We have Viron, who is providing heat networks, microgrids, and hydrogen. Basically everything that has to do with networks but isn't regulated yet. No, we have the telecom, which is wireless and fiber connectivity. Then we have Kirion, which is basically the consultant consultant company, which have a lot of knowledge about engineering and sustainable tech and infra. Then we have Kenter, which is the metering company, and they deliver energy management services. And then we have Entrance. Entrance is basically a platform. They created a platform where we can allow the companies to provide energy transaction services. So we, yeah, that's basically, I think, in short, what Aleander is for.
Thank you for that, Lars. Now let's move on to the core of the webinar. As I said, the topic for today is the learnings from the practices used to integrate renewables in the UK and the Netherlands. So the agenda for today is we'll start with an introduction on the topic and the research scope, which will then be followed by a more in-depth discussion on the main technical challenges associated with integration of renewables, which will then lead to a discussion on some of the practices that we've seen being implemented, and finally a summary and a brief discussion on the future direction of networks. That being said, let's start with the scope. So as I mentioned before, this presentation and the report that draws its highlights from has to do with the integration of renewable power generation. So by that we mean that within the scope we don't necessarily directly include the following. First of all, the integration of low carbon heating and transport technologies. By that I mean that it is still part of the narrative, for example, as a solution, because a lot of these new technologies have inherent flexibility and can be useful for the integration of renewables, or for example with regards to their implications for the future complexity of the system. However, we do not say specifically look at what we can do to, for example, install a very big EV charging fleet at a certain place. What are specific technical challenges with regards to that? We also left somewhat out of scope the challenges at the DSO level and at the system level to bring down the scope, but I felt that it is important to raise this issue at the beginning, because it is important to keep in mind that the solutions for many issues at the TSO level or at the system level will often be derived from distribution network assets. So I'm referring to things like system balancing or frequency response here. So it's important to keep in the narrative, especially as I guess the traditional lines of networks and the breakdown between distribution and transmission are becoming less clear than ever. Finally, with regards to geography, the research focused on two countries, the Netherlands and the UK, both of which are relatively advanced in their energy transition. That being said, I have a slide ready next that is a good summary of where these countries are in regards to energy transition and the installation of renewables. So on the left-hand side, you have some statistics on solar PV installations. So you have the installed base of solar PV in the Netherlands and in the UK. This has been normalized by the country population, so to reflect, I guess, the relativeness of the capacity installed versus the overall size of the country and the required capacity. I have also left out the utility scale installations here because these would not necessarily be installed in distribution networks. And I also have a similar graph on the right-hand side with regards to onshore wind. So some observations from these graphs. we see that both countries are fairly advanced with regards to onshore wind capacity. The UK is slightly ahead there, but there is some difference in regards to solar PV. Now the low figures for UK don't necessarily reflect the overall size of the PV installations. It's also a function that in the UK solar PV installations are mainly on the utility scale side rather than the residential and commercial and industrial. So about 3/4 of the market in the UK is utility scale solar. This is not the case in the Netherlands, where this represents only about 15%. Yeah, that's one, I guess, clear difference as an early observation. And I guess another thing that becomes obvious immediately is the remarkable growth for the solar PV market in the Netherlands over the last 5 years. And Lars, I would like to get your view here as a Dutch expert. If you can let us know why is this currently happening at this rate, and whether such a high rate has increased the challenges that Dutch DSOs face.
Yes, well, I think that one of the bigger reasons that we do have relatively a lot of PV installed here is because there are a lot of arrangements created by our government to create incentives for private individuals and companies to install, especially solar PV. The biggest example in the Netherlands is net metering. So we do have net metering as one of the few countries in the European Union. And it seems to be working because you can see the capacity of installed PV installations is very big, relatively, also responding to the UK. Next to net metering, we have a lot of a subsidized system, which is mainly created the last few years because there used to be a lot of amount of money available for biomass. The resistance against biomass increased, so there became a lot of money available for solar PV and wind, of course.
And I guess this also highlighted the challenges for Dutch DSOs as well, and such a high rate of installation. I guess this also serves as a nice introduction for the next part, where we're going to speak about the main technical challenges in networks. Let's see at the main technical challenges, and let's start by looking at the challenges together with the technology mix at each system level. We'll start from low voltage networks to go then to medium voltage, and then to high and extra high voltage networks, and discuss briefly the main issues related to networks and the integration to renewables. So starting at the low voltage level here, the dominant technology is definitely rooftop solar PV. So the challenges are heavily linked towards that, and they are especially evident in weak rural networks that are served by small distribution transformers. In these cases, the voltage rise from power generation may lead to voltage levels surpassing the upper acceptable limit at certain points of the network. So voltage management is becoming an issue. Power flows will sometimes be bidirectional over some parts of the low voltage circuit. So this means that also the voltage profiles will vary along the network. Another issue relating to solar PV and low voltage networks is that many of the installations use single phase inverters. So which could result in a disproportionate number of connections to be connected in one of the three phases. And therefore, there may be some phase imbalance in the system, which further makes voltage management further more difficult. A final point also here is the harmonic distortion. So this is mainly related with inverters that are, I guess, of a somewhat lower quality with regards to how they can manage harmonic distortion, and of course this could have implications for networks with regards to derating cables, lines, or transformers. Moving on to medium voltage. So here things start becoming bigger. So the scale of solar and wind installations increase, we start to have solar farms and wind farms that go up to some low megawatts in terms of capacity. This would also be where some bioenergy plants might be connected. But starting off with the wind and solar PV farms and their connections to the medium voltage network, again here we might have some reverse power flows, which may also result in the thermal ratings in some of the feeders being exceeded under scenarios where there is high power generation from renewables and low local demand. Especially this is the case in cases where there is a line drop compensation for the voltage in place, which would basically make things worse for the voltage management. There are also some I guess more minor talents which are shown in the smaller boxes and not smaller font. So these here are specific to the integration of synchronous and induction generators. So I'm speaking about the default current here. So these types of generators you would typically find in bioenergy plants or tri-generation, co-generation plants. And especially in urban settings, this may result in heightened fault level. So this is, I guess, a minor challenge when compared to wind and solar related issues, because by default this market is relatively smaller. And yet another smaller scale challenge is the fact that due to the high demand for new connections by renewable energy developers, substations might not be able to incorporate those new connections, and it might require some more space. There may be space limitations, which would need an additional civil works to incorporate this new generation. Then finally, to high and extra high voltage, similar issues here as well, just bigger overall installations, and the issues are mainly in areas which are concentrated by high wind and solar PV farms, which can result in generator-dominated networks, and where power flows are basically dominated by generation export at certain times. Now, I'll take a pause here, and I would like to ask you, Lars, with regards to the Netherlands and I guess its current situation. How do you see any of these challenges being particularly evident at the moment? Where are your main issues, I guess, in the grid at the moment, and what is the current trend with regards to the challenges?
Yes, so in the Netherlands we see increasing number of voltage and capacity problems in the low voltage grid, mainly occurred by solar PV. This results in a lot of grid reinforcement or smarter solutions. Next to that, we also have a lot of voltage and current issues in medium voltage grids too. We're working on a lot of like smart solutions to give customers still access to the grids and allow them to transport energy, like curtailment.
Thanks for that, Lars. And I think now it's the right time to move to the practices that we saw being used. So next chapter, practices. So this table summarizes the solutions to the challenges, and I believe that these can be largely grouped in two categories: network facing and customer facing. By network facing, we mean any solution that is related to a direct investment from a DSO into new equipment or to upgrade their network management capabilities. The solutions here that we list are obviously not exhaustive. They're just some examples of the solutions we discussed on the report. But yes, this includes things like soft meshing, dynamic line ratings, distribution transformers with automatic voltage control, and as you can see, we have grouped them according to which elements of the network they relate to. So if they are related to the low voltage, medium voltage, or high voltage. Obviously, some have wide wider implications and cut across some of these segmentation. The second type is customer-facing flexibility solutions, which is something that has emerged as an answer to many of the challenges to renewable integration. And yeah, in the next few slides, we'll just look at some examples of them in a bit more detail to help the discussion go forward. I will start with the enhanced monitoring. So here I want to point out the importance of monitoring as a solution, or if I might put it in a better way, I wouldn't call it necessarily a solution, but it is a very important enabler for many of the technical solutions. So a lot of the issues relating to the energy transition have now started to reach to the low voltage network level, especially, and this was the parts of the network that traditionally had the lowest visibility. And what we have seen happening more and more is that this visibility is now being increased. This is done for example, by replacing the traditional maximum demand indicators at a medium voltage to low voltage substation to be replaced by more sophisticated monitoring that looks at busbar voltage, feeder loading in detail, and the harmonic distortion on this level. This at the same time can be complemented by data from smart meters. So smart meters basically, and the more advanced the country is with regards to their rollouts, they will inevitably just give the option to DSOs to be able to monitor data at a level that they have never done before, and so that they can have visibility at parts of the network that are further down the line in a feeder. So, for example, you could get data on power flows or voltages from the smart meter data, and overall, the visibility on the network, on LV networks, will increase. But of course, the goal of increasing visibility and monitoring in networks expands to, I guess, more than just the low voltage and to at every single level. And without regards, let's see at dynamic line ratings, for example, because this also shows how the new tools that are available from the digitalization enable the implementation of solutions that are, from a wider technical perspective. So dynamic line ratings. So the whole concept is based that what used to happen traditionally was that the maximum amount of current that can flow through a conductor line was calculated statically. So you would assume as extreme static values for variables like wire tension or wind speed or temperature, to minimize the possibility of overheating of the cables. However, these calculations can be done more dynamically when also combined with monitoring systems that estimate the capacity on a real-time basis. And this is an attractive alternative because if you think about it, the capacity limit for a dynamic line would be bigger when it's cold, cold and windy day, and low in a hot and calm and sunny day. And this pairs in well with the way that wind power output is taking place in networks. So you would have high generation in those cold, windy days, where also coincidentally the capacity for the line would be higher. So by making sure that you can estimate this in a real-time accurate way, you can avoid basically reinforcing a line that didn't need to be reinforced, and so the overall connection for the wind farm would be cheaper and faster from a developer point of view. Now, moving on to some of the customer-facing solutions. Let's start with the demand-side flexibility, which involves basically agreeing demand-tier down contracts with customers to manage network constraints. And Lars, here I would like to ask you to give us an overview of how you use this type of flexibility in the Netherlands, and how this can help integration of renewables?
Yes, in the Netherlands we used to have something called congestion management. We used it on like a high voltage level with a lot of big customers, and now the DSO and the regulator is working on creating congestion management, or creating the principles of congestion management also for the medium voltage level with the a lot of smaller customers. What it says here, GoPax is something that Aleander created together with the other DSO and TSO in the Netherlands, and it's basically a platform where congestion management can be executed. It's a platform where the particular operators in the congested area can request or upscale power for a specific moment during the day. So, for example, we as Aleander can say, okay, in that specific area in the northern part of the Netherlands, we need to reduce like 2 megawatts tomorrow for during 2 hours or 3 hours. And then parties in that specific area can make an offer for to reduce the power for that time slot. Multiple parties can do, and then we as Aleander can choose for like the cheapest offer. And they will be asked to reduce their power. One important thing is that we have to do the opposite action, so reverse action in another area where there's no congestion, in order to stabilize the grid. I think in the future we expect more of this kind of solutions to in our grid. We expect it to grow. Because the power demand is growing very fast in the Netherlands, and we can't reinforce the grid in time. So we expect a lot of places where there will be congestion management in the future.
Thanks for that, Lars. And I guess another related issue with flexibility is, I guess, a different sort of flexibility which is centered around the renewable generator. So we're not looking at flexibly management of loads on the demand side, but on the generation side. And yeah, here, I mean, if you can give us a brief overview of how Aleander is approaching this and what types of offers are available for renewable energy developers in the Netherlands.
Yes, so in the Netherlands, like I said before, there are a lot of congested areas, so areas where there's no transport of energy possible. We also do have quite a lot of customers who we have to tell, okay, we can connect you to the grid, but you're not allowed to transport the energy you're producing. We call it transport restrictions. So they basically are connected to the grid, but not allowed to transport their energy until we reinforce the grid. We do have a lot of customers, and we still want to try to help them customers and help the business case and help to get more renewable energy into the grid. So we worked out quite a few solutions. One of them is active curtailment. For example, we use the actual power flows of the transformers as an input signal for wind and solar. So if the load of the transformer increases and we reach like the upper limits of the transformer, the capacity of the transformer, we will curtail the solar or the wind farm. We could change the input from the transformer also to, for example, a cable or the voltage at some point in the grid to reach the same effect. So it's basically what we're doing with active curtailment. Then we have non-redundant connections. We basically use the transport capacity of all of the transformers available at the substation for solar and wind farms. For example, if there are 3 transformers available, then we use all of them to transport solar and wind energy. If we have problems with one of the transformers, or we have to do maintenance on one of the transformers, we will curtail the production of the production units until the maintenance or the non-availability of the transformer has been done. We see in our data that the transformers, the overall availability of the transformers is like 99% of the time. So only 1% of the time, yeah, they're not allowed to transport their energy. That's basically a good idea. We even see that the benefits of the solution are higher than the costs. So it seems like a good business case to us. Even earlier this year, our government has given us their permission by law to do so. It used to be forbidden, but it's now fully permitted.
Okay.
To do this permanently, actually. Then the third one is time-based contracts. So, for example, in some places we don't have any non-restricted grid capacity available. So we give our customers the possibility to use the capacity which is available. For example, during nighttime. So if the grid is congested during daytime, but we do have capacity during nighttime, we give some customers, like example, customers with electric transportation companies. We give them capacity during nighttime. Well, during the day, the buses are driving all around, transporting people, and during nighttime, they will be recharged for the next day. So for them, it's not a problem. For us, it's not a problem. So it's really a good solution. We call this non-firm contracts. And then the last one, automatic voltage control for generators. It's basically when there are over voltage problems in the grid. Then we ask customers to install the automatic voltage control, where the reactive power consumption or production can influence the voltage level of the grid. Now, well, some parties are allowed to the grid if they agree to use this solution. And yeah, of course, the power plant will automatically curtail if the voltage level rises too high. So basically, 4 examples of the solutions we're using at the moment in the Netherlands.
Yeah, so and I guess the concept here is that the developer needs to accept, I guess, some of the risks around these flexible curtailment, to get faster or cheaper connection, basically. So it's I guess it's a process of accepting risks from a developer's point of view.
Yeah, true. So normally they aren't allowed to the grid, so that they get transport restrictions and they aren't allowed to transport their energy until the grid is reinforced. And now we say, okay, we can allow you to transport energy based on this condition until the grid is reinforced. So most of them are temporary solutions.
Good, thank you, Lars. That was a nice overview of the many options for flexible arrangements in the Netherlands. I'm also conscious of time, so let's move on to the final outtake, final outtakes and the future direction. I think this graph summarizes, I guess, nicely where the networks are currently at and their evolution in time, if you want. So if you look at the sort of conventional way of operation, things were very rarely happening real time, and there weren't many customer-facing solutions, and the overall customer engagement was low. So we were basically mostly on the sort of bottom left side of this graph. With the evolution of active network management, a lot of the actions have started to become more real time and evolve. And I guess the final part of this evolution comes with the flexibility markets that are now emerging all around Europe, but also especially in the UK and the Netherlands, where we see more and more of those customer-facing solutions being implemented and more transactions and actions happening on a real-time basis. So overall, there is, I say, a shift from the old centralized type of control and the conventional type of network-facing solutions to, I guess, a more autonomous, if you want, type of management in the systems. Now, with regards to some key outtakes from the report, here are some, I guess, 4 bullet points that we have highlighted. So first of all, I mentioned this also in the presentation on the importance of increasing monitoring and control capabilities in networks, because this is a very key enabler for the sort of evolution towards a real-time system, but also for other technologies that can help with the challenges to renewable integration. Then we also highlighted the role of flexibility, and we saw that a lot of the integration currently in both countries is taking advantage of flexibility, and especially on the generator side. Here, I guess the argument is also that because of those these technologies, solar and PV, typically have relatively low load factors. So curtailment is not a very frequent requirement anyway. So maybe the contract is there and the developer has accepted the risk, but the reality is that it's not something that is being enforced very frequently. Another observation is that the solutions and the issues, and therefore the solutions so far are mainly targeting the sort of medium voltage and high voltage levels, and this has to do with I guess how the integration of renewables happened historically, because the residential PV market is growing and everything, but still the penetration on a house level hasn't reached levels that it has become too problematic yet. However, the overall transition and how new loads like electric heating and electric transport come in line will definitely increase the challenges in low voltage networks as well. And finally, with regards to the differences between the two countries, I'd have to say as a final observation that there aren't many key differences, that there aren't any fundamental differences. I'd say the approach is relatively similar. Of course, there are differences in where you would see some solutions emerge or some issues being as important as in other places, but this would have to do with things like the energy mix in the country, or for example, as we mentioned, solar PV in the Netherlands, or for example with the characteristics of the network in each country. So how often do you see rural networks, for example, or how frequent overhead lines are. So that was today's presentation, and let's see also another final poll before we stop. So I would be interested to hear your opinion with regards to how ready are DSOs to facilitate the energy transition. So I realize there is huge amount to do. So the question here is, will they act as a brake for the energy transition, or will they be able to sort of facilitate and not act like a brake? I'll give you a few seconds for you to vote, and we'll see the results. Okay. So interestingly, about 3/4 answered that there's a possibility that they can act as a brake for the energy transition because of the huge amount of work that needs to be done to integrate those new technologies. So to me, this is a very interesting result, really, and yeah. So yeah, I'm conscious of time as well. We went a bit over time with the overall presentation. So before we go to questions, just very briefly to close with a bit about us. So in case of that you weren't aware, that Delta is also doing a series of podcasts which is called Talking New Energy, with weekly episodes hosted by our director, John Slow. If you found the webinar interesting, I'm sure you will find many interesting episodes to listen to within the series. This is a slide on Aleanders and some KPIs. I'll just go through quickly everything. This is on our new distribution network service. If you're interested in learning more about it, you can visit our website and read about it, or contact Arthur or Martijn with questions about what the service is about. And what the service includes is our typical mix of data research, of in-depth reports, viewpoints, databases, and all of this, of course, with the focus on distribution networks and their role in the energy transition. So thank you for joining the webinar. I don't think we have time to cover questions as we went a bit overboard, but thank you so much for joining, and we'll answer to your questions at a later stage. Lars, thank you for joining me on this webinar, and yeah, I hope you found it all interesting.